Hi, in this video we will learn electric current and then we will move to resistance and Ohm's law. Also we will learn about connecting resistors in series and parallels and also Kirchhoff's rules, and we will move to direct current circuits afterwards, and then we will also talk about RC circuits. So let's get started. Electric current is the movement of charged particles. So the charge may be Q in time t. So it's movement of charged particles in time t. So you have a bunch of charges and they move within the cable for a given time. So the electric current gives you that it quantifies how much charge passes through the wire per given time. So you can think of also a current in a river, for example. So in a river, water flows. So in the context of a river, you would talk about how much water moves in a given time. So that would give you the current of water. But in the context of electric current, it's basically the movement of charge per time. And the SI unit is here charges in units of coulomb and time is in units of seconds. And we can call coulomb per second A, which stands for ampere. Electric current occurs due to a potential difference, which is also voltage. So you have to connect a battery or some potential difference source, some electric source, so that it will provide the potential difference and the current will occur. If there's no battery or a similar source, then there will not be any current. So delta V, which is the potential difference, may be created by a battery or by a capacitor or electric generator. Electric potential difference, delta V, is like gravitational potential difference. And electric current I flows from high potential to low potential, similar to water flowing high to low gravitational potential. So let's look at this figure. So these two people, they are holding a garden hose which is filled with water, but the water, if the ends are at the same level, which means it's the same they have at the same potential, gravitational potential, then the water will not flow, even though there's some water. So the hose is filled with water, but it would not flow because the ends are at the same gravitational potential. But if one of the person lowers the hose, then as you can see, water flows. The reason for that is the water within the hose, it flows from high potential. So this is at a higher height. It flows from high potential to low potential. So it's a similar situation in the case of electrical circuits. If you need charges to flow in the wire, you need to create, of course, not gravitational potential, but you need to create a electric potential. So that potential is created by either a capacitor, battery, or electric generator. So in this example, let's do an example related to current, electric current. A CD player is connected to a battery that supplies it with a current of 0.22 amperes. So this is the current. How many electrons pass through the CD player in 4.5 seconds? So we will use the formula that we learned, definition of current. So we know the current and we know the time. So from here, we can calculate the charge. So before we move to how many electrons, we actually have to calculate the total charge that passes through the wire in 4.5 seconds. So we can rearrange this to write it as delta Q, the charge that is displaced, times, it will be equal to current times time. So current is 0.22 multiplied by the time, and this is the total charge that passes through or displaced or moved within the wire in 4.5 seconds. Now the next part of the question is determining how many electrons would make up this much charge. Now, one electron, the charge of one electron is 1.6 10 to the negative 19 coulomb. So if you divide the total charge to one electron charge, then it will give you the number of electrons. So the charge here is 0.99 and divided by this number, which is the charge of one electron, and it gives you 6.2 10 to the 18 electrons. So this is the number of electrons that passes through this wire in 4.5 seconds. So potential difference, delta V, it can be created by a charged battery, capacitor, or generator. That potential difference is needed for electrons to flow. If there's no potential difference, no battery, you will have electrons in the wire. But they will not move. Notice that the battery does not create charges. The charges are fixed. The number of electrons on the wire, they are fixed. The battery does not create electric charges. It just moves them, just like in the case of water in a hose. If you want to move the water, you can either connect, for example, you can connect some pump to the water to the hose or to the pipe, and that pump would not create water, but it would just move the water in the pipe or in the hose. So basically the potential difference created by the battery, it moves the electrons in the wire. Okay, so here what we have is in this diagram, we have this circuit, electric circuit. There's the battery and there's the resistor and there's the LED. So this LED gives out light, and more realistic picture is here. So you have the battery, you have the resistor, and you have the LED here. So if you connect the battery like this, what will happen is there will be some potential difference between the positive and negative. So if this is 5 volts battery, you will have 5 volts and 0 volts. And remember from the chapter 20, these numbers can change. So what matters is the potential difference is 5 volts. So you can write it as 0.5, or you can write it as 5 volts, 10 volts, or even, let's say, 0 volts, negative 5 volts, doesn't matter. So you can, as long as the difference is 5 volts. So this battery is a 5 volts battery. So it will create a potential difference between this point and this point. So what will happen is the electrons in the wire and also within the battery, they will move from low potential, where's the low potential? Here, 0 volts. Through the wire, they will pass through the LED and also the resistor, and they will come to the high potential position, high potential point. So the reason that the electrons are moving from low potential to high potential is because they are negatively charged particles. So negatively charged particles, they move from low potential to high potential. And if you remember from, again, chapter 20, if you have two plates, one of them is negatively charged, the other is positively charged. So this is high potential. So let's say 5 volts, and let's say this is negative 5 volts. If you have a positively charged particle, it would move from high potential to low potential. So it will move this way, and it makes sense. It's repelled by the positive charges and attracted by the negative charges. But if you have a negatively charged particle, it will move from low potential to high potential, so this way. And in terms of charges, it again makes sense because the positive charges will attract it and the negative charges will repel it. The same thing here, you can also think of this way. The negative charges would be attracted by the positive pole or would be repelled by the negative pole of the battery. So what flows in the wire, what we call electricity or electric current, it's actually the flow of electrons, because the atomic cores, the nuclei of atoms, they cannot move. They are fixed in their position. So what can move is only the electrons around those atoms. And when do they move? Well, you need a potential difference to be able to move them. Now, this one, what I showed here, it's a correct connection. But if you connect both ends of the wire to the same pole of the battery, what happens? Well, both of them are connected to the same pole. So these two wires, or the terminals of the wire, they are at the same potential. So here, delta V is 0, so there's no potential difference between them. But here, the potential difference between this point and this point, it was 5 volts, so that we would get a current flowing. But here you cannot get a current flow because the lead terminals, so this terminal and this terminal, they are at the same potential. Same thing would happen if you connected both of them here. So it doesn't matter if you can have even 100 volts or 1 million volts. If you connect the wires at the same terminal, they will be exactly at the same potential, but for the current to occur, you need a potential difference. So potential itself is not enough. You need potential difference between the wires, between the terminals. So if you look at here, again, the same problem. So these bulbs, they are like little resistors. They are like this. So this is the glass. So they have two terminals. And one of the terminal is down here at the bottom, and the other terminal is on this side. So both of these, so the bottom and this side, they should be connected to the different poles of the battery. So this one is a wrong connection, and this one is also a wrong connection, because, well, two terminals are connected, but they're connected to the same pole, so there's no potential difference now between the terminals. But this one is the correct one, because the bottom terminal is connected to the positive and the side is connected to the negative. Or you can do it other way. You can connect the bottom to the negative and side to the positive. That would also work. So, but the bottom line here is, what you need is, between these terminals, you need a potential difference. It's not enough to connect those to the same pole. So it's not, so at this point they will be at some potential, but because the potential, these two wires, they will be at the same potential, so that means delta V is 0, so that would not create electric current. So the bottom line is, you need potential difference for the electrons to flow, which is electric current. So electric current is defined as the opposite direction of the flow of electrons. So in the previous slide, we showed that electrons go from negative terminal. You can think of this way, the negative terminal pushes electrons away, or you can think of this way, the positive terminal pulls the electrons to itself. So the electrons would flow this way. So they would go from the filament and then heat up the filament because of the collisions of the electron with the atoms here, and then it would give light and also heat out, and then the electrons would come back to the positive terminal. But the definition of electric current it's defined historically as the opposite direction of the electron flow. So in this case, electrons are flowing counterclockwise, so they go this way. But the current, electric current, is defined in the opposite direction. So the electric current is defined clockwise here. In other words, we always consider electric current to go out from the positive terminal this way and go in the negative terminal. So this is just a definition. It's a historical definition. Back in the days, probably people thought that current is carried by positive particles, but the definition is it's stuck, so we have to use this definition. The bottom line is its electric current direction is defined as the opposite direction to the flow of electrons. So let's go with the analogies again between the electricity and other mechanical or water setups. So the person here is like battery moving water from low potential to high potential. This person takes water from here and raises it. So it's moving water from low potential to high potential, and then pours the water here, and the water flows and it turns this paddle. And if this paddle is connected to some generator or some other thing, it would create some work or even electricity. So this person is doing work here. So this person is like the battery. It creates potential difference. Water here is like current, and the paddle wheel is like the electric motor. So the water would turn this paddle wheel, which is similar to the case where in this circuit where the electric motor is connected to a battery, and a battery would create potential difference. So, and that would create electrons or the current to move, and when current moves through this motor, it would create mechanical work. So a battery uses chemical reactions to produce potential difference between its terminals. This is the positive terminal and this is the negative terminal. It causes current to flow through the motor, similar to the way the person lifting the water causes the water to flow through the paddle wheel. So these two are similar. So this potential difference is historically also called electromotive force. It's shown sometimes abbreviated with EMF, electromotive force, and it's shown by the Greek symbol letter epsilon. And before we move on, do not confuse it with vacuum dielectric permittivity, which is shown as epsilon 0, that we showed this in the previous lectures. So for all practical purposes, EMF, electromotive force, is the potential difference that a battery, capacitor, or a generator create between its terminals. So it has the same units as volt. So whenever you see this EMF or epsilon, think of it as the voltage that a battery or capacitor or a generator produces. So it's not something different. The amount of work it takes to move charge Q from the negative terminal to positive terminal. So let's say we did some similar questions in the previous lecture. So let's say we have positive and negative plates. They would create potential, so there would be some potential difference between them and also the electric fields. So in this case, electric fields would be from this way to the left, from positive to negative. So if you have a charged particle here, so to move it to the left or to the right, you would spend or gain some energy. Now, what is that energy? That energy would be, so the work done, it will be change in potential energy. Remember, these potentials are different, V1, V2. So V2 is definitely higher because it's the positive side is this way. So, and when you put a particle in the background of potential, it would have, when you multiply the charge of the particle by the potential in the background, it would give you the energy, the potential energy of that charged particle. And this relation here, this part, it goes back to mechanics. The work done here, we are interested in just the magnitudes, not the negative signs. So the work done is equal to change in potential energy. And in this context, the potential energy change is the charge times change in potential. So by using this formula, we can calculate how much energy is needed or how much work needs to be done to move a positively charged particle from here to here. So we will first calculate the potential difference. In this case, it would be V2 minus V1. And we would multiply the charge Q, and it would give us the change in potential energy, which is the same thing with the work done, or work needs to be done. So sometimes instead of potential, you may see epsilon, but the idea is the same. Electromotive force or potential or the voltage difference, they are the same things, just different names. So this figure shows the actual path of electrons in a wire. So when you have a wire, if you zoom in and if you look at the electrons, it actually hits to the atoms. So it's scattered. So it bumps into the atoms, and its path constantly, it makes these zigzag motions. It moves in, so this is the positive terminal, so the current is this way. But remember, electrons moves in the opposite direction to the current, so that this electron moves this way. So it moves in the wire, but it makes some collisions throughout that motion. So even though the average motion is forward, but if you look closely, it makes some collisions with the atoms in this wire or in this resistor. So electrons bump into other particles in the material, which are actually atoms, and hence they feel resistance as they flow in a conductor. So if these collisions were not there, if the electron does not collide with the atoms, it would just go straight, right? It would really quickly, it will be able to go straight quickly. But because of these collisions, the electron still moves forward, but it takes some time. So it feels some resistance. So this is then, in fact, the source of resistance in the wires or in the circuit elements that are called resistors that we will see in the following slides. The resistors, they're shown like this in the circuit as circuit elements. And so basically these collisions are the reason of resistance. And in fact, by means of these collisions, when you have a heater, we get heat. And also when you have the light bulb, like this. So these collisions again create light. So that light it comes out from the light bulb. So by means of these collisions, we are able to get actually light and heat from the circuits. So it's not always a bad thing, but it depends on the situation. So Ohm's law relates the voltage, the current, and the resistance. So now we have the wire or a resistor like this. So it has the resistance R. So this quantifies how much resistance would the electrons or the current would feel. And it depends on the material. So it's different in copper, it's different in gold, it's different in aluminum. So it depends on the material. And also the length and the area of the material of the resistor. We will come to that in the following slides, but for now it's just the Ohm's law. It relates, so V equals IR, it relates the voltage, here basically the voltage coming from the battery, to the current in the circuit, to the resistance of the resistor. So the unit of resistance, you can see it from here, R is, so R equals V divided by I. So it's voltage divided by ampere. But we can show it with capital omega letter, Greek letter, omega, and we will call it just ohm. So that's the shorthand of showing voltage divided by volts divided by amperes. The other thing is that in the circuit, so we will have circuits like these, so there will be some resistance, maybe some other circuit elements like a capacitor, and maybe a battery like this. So we will only consider the resistance of this resistor. So the wire itself, in reality, all wires, they have some resistance, but these wires, we will assume when we do the circuit analysis, we will assume that they have no resistance. Okay, so R in the Ohm's law that we just learned, V equals IR, is called resistance. Its unit is in ohms. And it depends on the length, area, and the resistivity, rho, this is Greek letter rho, of the material, of the resistor or wire. So this resistivity, it depends on the material. For example, for insulators, insulator means the class of materials that do not allow the current to flow. So they don't allow electric currents. For example, quartz, rubber, glass, as you can see, the resistivities are huge. So, and it makes sense, they don't conduct electricity. But if you move to conductors, the resistivities are really, really small. You can see that, the values. So in this table, for example, which one? So copper and silver, they have the least resistivities. And in fact, most of the cables or wires, they are made of copper. So if you make a resistor, so you may choose any material depending on the value of resistance you want. But if you make just straight wires, just to connect circuit elements, you would want to use the material that has the least resistivity, because you don't want the wire to create heat and waste energy. Okay, so in the Ohm's law, we have this R resistivity, but how do we determine it? If we are given the resistance, R is resistance, how do we determine it? Well, this is the formula to determine it. If you are given the resistivity of the material, you plug in here, and the length of the materials here, and the area in the denominator. So if you have a longer and longer materials, it will create more resistivity. Sorry, it will create more resistance, because the electron would bump into more and more atoms because it's longer. So the length of the resistor and the resistance of the resistor, they are directly proportional. But if you look at the area, it's inversely proportional with resistance. The reason for that is if you have a larger area, then it will be easier for electrons to flow by making less collisions with the other electrons. So smaller area means if you have a small area, you need to pack more electrons, you need to force more electrons in a small area, so there will be more collisions between the electrons, so it will create more resistance. If A is small, it will create more resistance. Okay, let's look at the example. A current of 1.82 amperes flows through a copper wire of 1.75 meters long. So this is the L value. So here the current is given. And the diameter is here given. This is the diameter. So remember, diameter is, so if this is the radius, diameter is the whole thing. So D is equal to 2R. So find the potential difference between the ends of the wire. So we have this wire, let's say, and the value of L and A, well, A is not given, but we can calculate it. So pretty much everything is given. What the question is the potential difference. So let's say we connect this to a battery. So here there's this potential difference. Now we have to find this potential difference, and the resistance is R. So how do you find it? You would write V equals delta V or V, the same thing here in this context. So I is given. So to be able to find V, I is given, but we need to find the resistance first. So we go back to this formula. So the resistance is, well, this is made of copper. So the copper resistivity is here, which is this value. And we will multiply by the length of the wire. And then we have to calculate the area. So for the area, it's pi r squared. Now, this is diameter in millimeters. So first we have to convert it to meters. So in meters, it becomes 0.0011 meters. And because this is diameter, we have to divide it by 2 to get the radius in meters. So this thing here is radius. So again, two things go from diameter to radius. So diameter divided by 2 is radius, and also convert millimeters to meters. So when you do this calculation, it turns out that the resistance of this resistor is 0.031 ohms. Now we can plug this in here. We already know the current, which is given in the problem here. So multiply the current by the resistance, and you will find the voltage difference that's applied to this resistor or wire. So when charge delta Q, so let's say this is amount of charge in coulombs, it's called delta Q. When it moves across a potential difference V, its potential energy changes how much? This much. We already used this even in the earlier chapters. The potential is related to charge times potential energy. This is potential energy is related to charge times potential. So this is potential energy. Therefore, the power it takes to do this, so what is the power required to move this much charge across the potential difference? Let's say we have, so potential difference may be coming from the battery. Let's say this battery has the potential difference of 1.5 volts. Now the question is how much energy, how much power is needed to move this much charge, to move on this wire from between the terminals. So how much power, how much energy is it's here, and how much power is needed to move the electrons from here to, from negative to positive terminal through this wire. So to be able to calculate it, we have to divide the energy by time. And the energy is defined here again, Q times charge times potential. Now, if you look at here, charge divided by time, we actually made the definition in the previous slides. This definition, the definition of charge divided by time. So how much charge passes through a point in a given time, well, that's current. So it turns out that the power is current times potential or voltage. And as usual, a SI unit of power is always watts. So when W is units, it's watts, but when it's used in the formula, as we saw, this was equal to the work done. So when it's used as a variable in the formula, it means work, but if it's a unit, it means watt. Okay, so in materials for which Ohm's law holds, so when Ohm's law is valid, it's valid almost all, in many situations that you will run into. Of course, there are some exceptions, but it's almost always holds. The power, so in that case, the power can also be written as, so here we learned that it could be written as I times V, but instead of V, by using the Ohm's law, we can write I times R. So if you write I times R here, what you get is I squared R. So you can write power as I squared R as well. The other option is, again, now instead of, so if you again use Ohm's law, but this form, I equals V divided by R. Now plug it here. So if you plug this here, so you would get V divided by R times V. So it will be V squared divided by R. So there are three forms. So this one, and this one. So they are equivalent. You can use any of these depending on the situation. For example, if R and I are given, it will be quicker to use this one. But if, let's say, resistance is not given, then instead of using these two, it will be quicker to use this one. So the energy spent, we talked about this a little bit a couple seconds ago. The energy spent by a resistor, it goes into heat. So for example, in the case of a heater, and also sometimes it goes into light, and that an example for that is the light bulb. So in both cases, you have resistors. So when the electric company sends you an electric bill, your usage is coded in kilowatt hours. So remember, kilo, it just means 1,000. So this means 1,000. Watts is, it's the unit of power, and hours is time. So this is like power times time. And if you remember from physics 1, power times time, it gives you the total energy used or produced. Remember, power is by definition is energy or work divided by time. But if you write it this way, so it means power times time, it gives you the energy consumed or produced. So the electric company, it bills you by the amount of energy that you use. So this whole thing, kilowatt hours, it's the energy consumed. And you can see in this electric bill from Seattle, you can see that the consumption is listed in kilowatt hours. So let's analyze this unit again, kilowatt hour. So kilo means 1,000, watt is watt, and hour is, if we convert it to seconds, the SI unit, 3,600 seconds. So, and when you do the multiplication, it turns out this is 3.6 10 to the 6 joules. And as you know, joules is the unit of energy. So kilowatt is, so kW is kilowatt, and it's the unit of power, P. Power is energy divided by time, multiplying it by time gives energy, which is kilowatts hour here. And just to get a feel of the wattage or the power of basic home appliances, for example, if you have a vacuum like this, the power is about 750 watts. If you have an iron, its power would be 1000 or 2000 watts. Similar, if you have an oven, electric oven, its power would be around 2000 watts. So let's do this example. A 100-watt light bulb. So this is the power of the light bulb. And the power is also related to how much light it gives out. So it's connected to a 110 volt outlet. So outlet is, it's on the wall. In Turkey or European countries, it's 220, but in the US, it's 110 volt. So this is the outlet on the wall. So a light bulb is connected. So the cost of electricity in Seattle is 8 cents per kilowatt hours. Now the first part of the question is find the electric current on the light bulb. Now, since the power is given, and we know this formula, and the resistance of the light bulb is not given, so we can use this formula. And from here, we can write current as power divided by voltage. So the power is 100 watts divided by the outlet voltage, 110, and it turns out the light bulb draws 0.91 amperes of current. Now the second part is find the resistance of the light bulb. Now you can use Ohm's law, V equals IR. So we don't know I, but we don't know R, but we know I, the current, and we know the voltage. So divide the voltage, 110, by the current, we just calculated here. And turns out the resistance of the light bulb is 121 ohms. Now, as I mentioned, this was one of the three options. There were other options to calculate power. And one of them was this one, I squared R. Let's verify if this also works. So I is 0.91 amperes. Take its square and multiply by resistance, and it gives you 100 watts. That makes sense because the light bulb that we had is 100 watts. So this verifies that this formula and this formula, they give the same values. Now, what is the cost of using this bulb for 90 minutes? Now, so here, the cost per energy is given in terms of kilowatt hours. So I can convert it to joules, but there's no need for that. So if you want to use this, what you can do is you can just calculate the energy in, again, in the units of kilowatt hours. So energy is power times time. Power is 100 watts. In other words, so 100 watts means this light bulb it would consume 100 joules per 1 second. So that's the meaning of it. And joules per second is watts. So this is equals 100 watts. So if it spends 100 joules in 1 second, and if I want to calculate how much energy it spends in 90 minutes, then I would just multiply by time and it would give me the energy. Except in this case, I will not use joules, but I will work with kilowatt hours. Again, this is in units of energy. So now, because here the cost is given in terms of kilowatt hours, I will try to make my units, convert them into kilowatt hours. So instead of 90 minutes, what I will use is I will convert it to hours. So it will be 1.5 hours. So if I multiply by the watts, the result will be 150 watts hour. again, so I try to make it the same unit with this cost, which is kilowatt hours. So if I add kilo here, which means 1,000, so and I have to divide it then, so divide it by 1,000 and add kilo here. So if you do this, it turns out it's 0.15 kilowatt hours. So this is the energy, so U is energy, that this light bulb would consume in 90 minutes. Now, if you want to calculate the cost, then multiply this energy by the price of the electricity per energy per kilowatt hours. So these two units, they will cancel each other, and if you do the multiplication, it turns out for 90 minutes using this light bulb, it will cost you 1.2 cents. Okay, now let's move to this section where we will talk about series and parallel connections. So how do you connect resistors in series and in parallels? Let's start with the series connection. So resistors connected end to end are said to be in series. So one resistor comes after another. So they're connected end to end. So that's called serial connection. So they can be replaced by a single equivalent resistance. So instead of these three, what I can do is I can actually make another circuit with just one resistor. And to be able to get the same current or the same effect, I have to use, now, which equivalent resistor should I use? Now we will answer that question. So the resistor that you have to use is, but before let's use Ohm's law to find it. So now the current flows in this circuit. So there's just one wire, one closed loop. So it's always the same current that flows. So in a circuit, if there's no splitting in the wires, as you can see here, there's just one wire that loops onto itself. So there's just one wire. So in this case, the current that passes through all elements, circuit elements, will be the same because there's no splitting. So there's no another wire that's connected here. So there's no current going out of this wire. So we have the same current passing through, as you can see. We use the same variable I. And that current we can relate that current to the values of resistance and also the voltage on each circuit elements. So the relation would be, so basically Ohm's law. So here for this one, the voltage V1 here is the voltage between the terminals of the resistor. So here voltage is this voltage. And V1 divided by R1, it would give you the current I. Same thing here, V2 divided by R2, it will give you the current I. So we are not using different I's. We don't say I1, I2, I3. The reason for that is it's the same current that passes through this circuit because there's no splitting. So instead of the circuit with three resistors, you can also build a circuit with just one resistor. But if you want, so for the same voltage source, if you want the same current I, then you have to use the resistance at a specific value that would stand instead of these three. So that value, R equivalent, is given by R1 plus R2 plus R3. So instead of using this circuit, let's say this is 10 ohms, this is 10 ohms, and this is 5 ohms. So instead of these three, what you can do is you can use a resistor with 25 ohms, and it would create the same current just like here. And this Req, it means R equivalent. So it's the equivalent resistance. And we will need to use this formula here to be able to calculate the equivalent resistance. For example, to find the current in the circuit. Let's say if this voltage source is, if the potential is 100 volts, then if you want to calculate the current, you have to find first the equivalent resistance. In this case, it's 25, and you would do V equals IR. So V is 100, so I is the current, and R in this case, you would use the equivalent resistance, which is 25. So from here, you would find I current to be 4 amperes. So this formula of equivalent resistance, it will be useful, as you will see in the following slides. Now, we can make some observations here. So when resistors are connected in series, first, something I already said, the current passing through each resistor connected in series, when they are connected in series, which means one after another without the wire splitting, it is the same. So the current here is the same. But if you connect another resistor, let's say like this here, wire, because now the current would split here, then we cannot really use we would not be able to say the current will be the same in all wires. But if there's no splitting like this, all the resistors are connected in series, then the current is the same. So the voltage on each resistor, V1, V2, V3, when you add them up, it will give you the voltage of the battery source. So if we have 10 volts here, 10 volts here, and let's say 30 volts, then you can say the battery or the voltage source is 30, 10, 10, it's 50 volts. So basically you add up the voltages. So again, the current is the same. We are talking about the series connection. Current is the same, but the voltages on each resistor, they add up to give the voltage of the battery source, battery or the voltage source. Now finally, as we mentioned, if you want the equivalent resistance, then all you have to do is to add them up. Of course, this formula is only valid in series. If they're connected in parallel, that we will see in a second, we will have a different formula. Now, here's an example. Again, these resistors are connected in series. If you want to find the equivalent resistance, you would just add them up. So it will give you 3R. So that means this circuit is equal to this circuit. So there's this 9 volts battery, and it's connected to this equivalent resistance, which is 3R ohms. Now, if you want to find, let's say, the current in the circuit, remember, so this long side of the battery, it's the positive side. The short side is the negative side. So high potential, low potential. High potential is drawn, it's longer, and the low potential is short side. So if you want to find the current in the circuit, now we can use this little circuit here. So we will use V equals I, R equivalent. V is 9 volts here. I is something we will calculate now, and the equivalent resistance is 3R. Now from here, if you divide both sides by 3R, you will find the current is 3 divided by R. So this is the current. Now the next question would be, what is the voltage difference on each resistor? What is the voltage difference on each resistor? So we can calculate it by again using Ohm's law. So to find the voltage, what you will do is you will multiply the current by the resistance. So for example, for this one, the current, well, the same current actually passes through them, through each other. So it's the same current for each one because this is series connection. The cable, the wire is not splitted or connected to any other wire. So it's just one wire. So the same current for each one. Resistances, maybe, in principle they can be different, but here in this problem they are also the same. So for example, for this one, we will multiply, the voltage will be the current, 3 divided by R, we found here, multiplied by the resistance, which is R, which will give you 3 amperes, sorry, 3 volts. So the voltage on this one is 3 volts. Same thing here. The current is the same, 3 divided by R. The resistances are the same. Multiply them with each other, so you will get again 3 volts. And also 3 volts here. Now what happens here is, at this end, so let's imagine that this is 0 volts. And this positive terminal is at 9 volts. So all the points on this wire is at 9 volts until the resistor. So this point is also at 9 volts. Now this resistor is using up 3 volts. So 9 volts when you come to this point. So this point then drops to 6 volts. Again, another 3 volts is consumed by or taken by this resistor. So at this point, the voltage on the wire drops to 3 volts. And another 3 volts is used, so it drops to 0 volts here. So on the wire at all points, if there's no circuit element interrupts the wire, then at all points it will be the same potential. And as you can see here, it's connected to 0 potential, so it actually checks out. So everything makes sense here. And you can also look at the voltages, what we said. So let's go back to the previous slide. So here, the second point, it says if you add up the voltages, it will give you the voltage of the battery. And indeed, that's the case. If you add up 3, 3, 3, it gives you 9 volts, which is the voltage of the battery. So we basically used all of these that we learned here. First, the current was the same on each resistor. We verified that the voltages, they add up to give to the source voltage. And also we calculated the equivalent resistance so that we can calculate the current on the wire. So to be able to calculate this current, we had to first calculate the equivalent resistance, and our circuit would reduce to this. And from here, since there's just one resistance, we could use V equals IR, which is the Ohm's law. And finally, for this slide, we were able to find the voltage difference on each resistor without knowing the value of R. So even though we don't know what R is, we were able to calculate the voltage difference on each circuit element. So we don't know R, we don't know I exactly. Well, we know the expression, but we don't know the numerical value. But we know the voltages, we know the numerical values of the voltages, even though we don't know the R. Okay, here is another problem. So in this case, we have 2 resistors with different resistances. So again, you would so to be able to calculate current, now the thing here is we will use V equals IR, right? So, but in this circuit, there are 2 R, so we can't really apply this directly. What we have to do is we have to find the equivalent resistance, which is 6 in this case. You just add them up and then draw this circuit again, 12 volts. Now we can apply V equals IR here. So I would be voltage 12 divided by the resistance 6, which is 2 amperes. So 2 amperes is coming out of this battery. So 2 ampere is coming out from the battery. And of course, 2 amperes will go in. So this current will not change. So let me go back here. So here what changes is 9 volts, 6 volts, 3 volts, 0 volts. And here it becomes 9 volts again after the battery, 6 volts, 3 volts, 0 volts. So what's changing here in series connection as we go over the circuit elements, in this case the resistors, it's the voltage. But the current at every point is the same in series connection. So the same thing here, 2 amperes is coming out, it's 2 amperes here, 2 amperes here, 2 amperes here. It's the same current. Now, so we found the current. Now the next is, let's calculate the voltage difference on each resistor. So what you have to use, again, the Ohm's law. If I multiply the current, 2 amperes, with the resistance, so 2 times 2, it makes 4. So here, 4 volts. And here, 2 amperes times 4 ohms, it makes 8 volts. Now let's verify if these two voltages add up to 12. Yes, they indeed add up to 12, which gives you the voltage of the battery. So at this point, you have 12 volts, and it drops to 8 volts because 4 volts is taken by this resistor. So at this point, you have 8 volts, and this resistor also takes up 8 volts. So at this point, you have 0 volts, and in that it's connected to the 0 volts side of the battery. Okay, let's talk about non-ideal batteries. All batteries are non-ideal. So what it means is they have internal voltage loss due to internal resistors. So even though you don't see any resistor connected, of course, there's no physical resistor, but because of the chemical processes, some of those chemical processes are not perfect and consume some energy, so you can model it as an internal resistance. So you can think of there is some internal resistance, and also there are some cables sometimes within the battery, so they also act as a resistor. So this is so epsilon here is the voltage or the electromotive force that the battery creates. But before you get it from the battery, so what the way that you get the voltage from the terminals, you get it from the terminals, but before it comes to the terminals, there is some internal resistance in the battery. Again, it may be caused by some of the imperfect chemical reactions that consume energy or that produce heat, or maybe there is the cables within or the metals within the battery, they may also create some resistance. Let's show it with lowercase r. So, and if you connect this battery to a resistor uppercase R, you would imagine using V equals IR. So let's use epsilon. So epsilon equals IR. So you would expect the current to be epsilon divided by uppercase R. But in fact, this is only valid if the battery is ideal, which means R, lowercase r equals 0. But in reality, lowercase r is not equal to 0. So if you look at this circuit, effectively you actually have two batteries and they're connected in series. What happens if you connect two batteries in series? Well, you just add them up to find the equivalent resistance. Now we have to use this with the Ohm's law. So the current is the voltage divided by not R as I did here, but it will be R, it will be the equivalent resistance, which is R plus uppercase R plus lowercase r. See this here, the current that you will get from this calculation is less than the current you would get here, because in the denominator, now the denominator is larger than uppercase R. Now the voltage on resistor R is, now let's say you calculate this current I, which is epsilon divided by uppercase R, lowercase r. And if you want to calculate the voltage here, let's call VR. Then VR is the current. Remember, the current is the same everywhere. The current, which is I, times lowercase r, which is here. And if you want to write it explicitly, so I is epsilon divided by R, uppercase R plus lowercase r, and multiplied by R, which is the resistance of this internal resistor. So if you want to write it here, so you can write the voltage on this internal resistance as this. Now this voltage, it eats up some of the voltage that's produced by the battery, right? So the battery cannot provide you epsilon, but it will only provide you epsilon minus IR. And again, IR is the voltage here, it's this voltage. So it's the voltage that's taken by this internal resistance. So what you get outside, so when you connect something to the battery, the voltage that you are going to get from the battery is not the voltage that it produces, but it's the voltage minus, so that epsilon minus IR, the volt, so this VR, which is equal to IR. So it will be less than, so the actual voltage is the voltage that you get from the battery, and it will be less than epsilon. So we subtract IR from epsilon because the internal resistance R wastes some of the potential that the battery provides. Battery provides epsilon, but this internal resistance eats up some of that potential. So at the end of the day, you get epsilon minus I lowercase r. Okay, so we are done with the series connection. Now we move to parallel connection. Now in this case, resistors are in parallel when both ends of resistors are connected together directly. So this is important. This directly, this word is important. So as you can see, this end of R1 is connected to R2, and the other end of R1 is directly connected to R2 as well. So we can say R1 and R2 are parallel. Same thing with R1 and R3, or R2 and R3. So the ends are not, so it's the same cable. Here, it's the same cable. So there's no circuit element in between. For example, if you put a resistor here, then these ends of these resistors, R1 and R2, they would be connected directly. But here, as you can see, this end of R1 and this end of R2, they are not connected directly because there is another circuit element in between. In this case, it's a resistor, or there could be, you can put a capacitor. So that would break the condition of parallel connection. So again, what you need for parallel is if you have two resistors or more, so these two ends, they should be connected and directly, which means there's no any other circuit element in between here. And also these two should be connected. So this is a parallel connection. So this is parallel, but these are also parallel. Okay, you can have some wire in between, that's no problem. As long as you don't have a capacitor like this or a resistor here, then it's still a parallel connection. So in this case, so the wire, having wire between the terminals of the resistors, it's okay. It doesn't break the condition of parallel connection. So in this case, we have 3 resistors connected in parallel. Now again, so when you're given the voltage, if you want the current that's coming out of the battery, you would use this V equals IR. But since you have different R's, not just one, then there's an ambiguity. What are you going to use for R? What you have to do is you have to calculate the equivalent resistance again. Equivalent resistance, and you basically reduce it to one resistance, and then here you can easily use V equals IR. So in this case, V would be epsilon, and I is the current, and the resistance is the R equivalent. So from here, the current would be epsilon divided by R equivalent. So we have to calculate this R equivalent. Now, how do you calculate it? Well, if the resistors are connected in parallel, again, we have 3 rules. So for parallel connection, so to calculate R equivalent, you have to use this formula. So let's say you have 2 ohms, 2 ohms, and 1 ohm. So what you would do is 1/2 plus 1/2 plus 1/1. So 2 ohms, 2 ohms, 1 ohms. So this is equal to 1/R equivalent. So 1/2 plus 1/2 makes 1, plus 1, it makes 2. So 2 equals 1 divided by R equivalent. So one of the common mistakes here is thinking that 2 is the R equivalent, but it's not correct. So it's 2 is equal to 1/R equivalent. So here, then R equivalent becomes 1/2. So you would use this equation. So once you find R equivalent, and if you know the voltage from the battery, then you can use Ohm's law to calculate the current that comes out of this battery. So the current that you calculate is not the current here. It's not the current here or here. What you are calculating as current it's the current that comes out of battery, and the same current goes into the battery. So you're calculating I from this equation by using R equivalent. To calculate the current on each resistor here, we have to use, we will have to be careful because the current here, as you can see, it splits. Here it splits into 2. So one of them is going down, the other part is going this way. And at this point, it again splits into 2. One part is going and some part is here. And the current does not split in half. So it splits according to the values of the resistors. So now we will go over that. But so these observations are again important. Now, so we learned how to calculate the equivalent resistance if they're connected, if the resistors are connected in parallel, as you can see here. Now, the second thing that we have to be careful here, the current passing through each resistor connected in parallel are different. They can be the same if the resistors are the same, but in general, they will be different. So that's why we are using E1, E2, and E3. Sorry, I1, I2, I3. And the current provided by the battery, it will be I. So that I that we calculated from here by using equivalent resistance, it will be the I that's coming from the battery, that's provided by the battery. Okay, and that I will be equal to, now as you can see, I comes in and it's split into 3 currents. So then I will be equal to I1 plus I2 plus I3. And those 3 currents, they actually combine, get together at this point, and then they become again I, and they go back to the battery. Now remember, when we talked about the series connection, we said the current is the same if it doesn't split up. So from this point to this point, it's always I, because there's no splitting here. You can have circuit elements, you can have resistors or batteries, but the current doesn't change. The current only changes if the cables split. You can think of current as water in the pipe. If the pipes split, if you have a fork like this, then the water goes down in each pipe, of course. So the same thing with electric current. So then the currents are not the same now. They are splitted, and the total current here provided by the battery coming out of the battery or passing through the battery is equal to I1 plus I2 plus I3. Now, the voltage is the same on all parallel circuit elements. There may be resistors or batteries. Now, the voltage, so as you can see, these resistors are parallel with each other, but they're also parallel to this voltage. So if you have the voltage epsilon here, then the voltage here is also epsilon on this resistor R1. The voltage here is also epsilon, and the voltage here is also epsilon. So when you have parallel connection, then the voltage is the same at all parallel points. If you remember the series connection, the current was the same everywhere, but the voltage was different. Maybe we can go back here. You can see that the current is the same, but the voltages are different. Or if you go back to this one, the values of voltages may be even the same, but in general they're different. You can see that. But the current is the same. But if you do parallel connection, now the voltages are the same in all parallel sections of the circuit, but now currents are different, I1, I2, I3. So these three observations, they're important for both series connection and also parallel connection. So, and maybe let's also talk about this. If you have, let's say, a circuit like this, let's say one battery here, one resistor here, and here, if you have two resistors, let's say this is again, let's say 3 volts. Now this 3 volts battery is parallel with this single resistor. So here the voltage on it will be 3 volts as well. Now if you come to this point, here 3 volts is actually from here to here. So from here to here. So it's not 3 volts on each one. So the total is 3 volts. Okay, let's continue with this example. Find the current passing through the resistor R1. So now the current will go from positive to negative this way. So let's call it I. So it will go in this way, I. Now at this point, it will split into two. So I will call it I1 and I2. So this I2 will go through here. So it will come here as I2 again. And this I1, it will not change, I2. Now, and at this point, at this junction, they will combine. So this is I1, sorry, this is I1. So at this point, they will combine to make I1 plus I2. And indeed, that's actually the definition of I. It splits into two, and those two combine to make, again, I. So I is equal to I1 plus I2. This is actually the rule, the first rule here. So the total current that goes through the battery is equal to the current on each section, on each parallel section of the circuit. Now, if you want to calculate the current here, you don't have to find I actually. You can do that by calculating the equivalent resistors, but you don't have to, because now what we are going to use is the second observation here. The voltage is the same on all parallel circuit elements. So if we have 10 volts here, then we also have 10 volts here, and we also have 10 volts here. So you know R, resistance, you know the voltage. Now use V equals IR. You know the voltage, you know the resistance, you can calculate I. So I1 will be equal to the voltage, which is 10 volts, divided by 5 ohms, and you will find it's 2 amperes. So 2 amperes is passing through here. And if you want to calculate the current here, again, do 10 divided by 2, it will give you 5 amperes here. Now, the next question can be, what is the total current here passing through the battery? Well, if it's split into 2 and 5, then that means it was 7 amperes. Now let's verify by using the equivalent resistance here if these values are correct. So to calculate the equivalent resistance, you would use this formula. So 1 divided by 2 ohms plus 1 divided by 5 ohms. So this would make 5 plus 2, 7 divided by 10. Okay, but I have to flip this, so R equivalent is 10 divided by 7. So now imagine we have a circuit like this. So again, 10 volts, and the equivalent resistor is 10 divided by 7 ohms. Now let's try to calculate current. Let's use 10 volts. 10 equals current times R. R is 10 divided by 7. Now these 10s cancel, and I turns out to be 7 amperes, which is exactly the same as we found here. So as you can see, there are multiple ways to solve circuit problems, but it's usually good to follow the easiest path. So in this case, if you have a parallel circuit, a circuit elements, in this case resistors, connected in parallel, then you can use the fact that the voltage on each part of the circuit will be the same because these are parallel. Okay, now let's move to mixed connection. Now, a collection of resistors, they can be connected in series and parallel, but they don't have to be either series or parallel. So there may be mixed connections, some of them parallel, some of them in series. So in this circuit here, A and B and the battery are in series, right? So A, battery, and B, there's no interruption between them. So they're connected in series, one after another. So this one, and this one, they are in series. And let's look at C and D. They are in parallel because the ends are connected to the same point, same cable. So C and D are in parallel. But let's consider A and C. So A and C. First of all, they are not in parallel. So one ends, they meet with this wire, but the other ends, there are interruptions. There's the battery, there's another resistor. So these two ends of C and A, they are not connected directly. Remember, the word directly was important. They're not connected directly because they're interrupted. That connection is interrupted by this battery and by this resistor B. So they are not in parallel. Are they in series? Let's see. So series means one resistor comes after another resistor. But if you look at here, so after resistor A, there's this cable, it splits into two as C and D. So if this is A, then we have C, yes, but there's also another cable that comes out, and it's for the resistor D. So in this case, we cannot really say A and C in series. They are not in series. So A and C they are neither in parallel nor in series. So there's a mixed connection here. As I said, a connection doesn't have to be either parallel or series. It can be a mixed connection. Now, but if I write the equivalent resistance for these two, so if these are R and R, let's apply the formula. They are in parallel. For parallels, we use this formula. So 1 over R, 1 over R, it makes 2 over R, but I have to flip this to find the equivalent resistance. So R divided by 2. So instead of these two, I can replace them by this resistor, which is R divided, of which resistance is R divided by 2. Then in this case, let me call it F. So in this case, I can say A, F, and B, they are in series. And if you take one more step to calculate the total equivalent resistance in the circuit, then see these three are in series. So when they're in series, you just add the resistances up, the values. So R plus R divided by 2 plus R, which makes 2.5 R. So this equivalent resistance is 2.5 R. So here, let's take a look at here. A and B are neither in series nor in parallel. So A and B, they sort of look parallel, but they are not. These ends are connected, that's good. But as you can see, this terminal of A and this terminal of B, they are not directly connected. There is C in between. So for that reason, they are not in parallel. Are they in series? Well, look at here. They're connected, but there's another wire that comes out in between. So think of this as A, and this is B. So they're connected, but there's another wire that comes out and it's connected to another thing, which is battery here. So because of this reason, they are not in series either. So A and B are neither in series nor in parallel. Again, for series, you would need something like this. So they're connected one after another, but there's no another connection or splitting in the wire. So this would be series, but this is not in series. Let's look at A and C. They are also the same thing, just like B. A and C are neither in series nor parallel. B and C, they are obviously in series. And A and the equivalent resistance of BC. So if you think of these two together and call this R equivalent BC, now we can say A and this whole thing, these two together, they are in parallel. Now, how do you calculate equivalent resistance here? Now these are in series, B and C. So instead of these two, so let's draw A here. So instead of these two, I can just put just one resistance here. So this one is R, and this one will be 2R. And here's the battery. And I will take one more step. Now I will calculate the equivalent resistance here. Now R and 2R, they are in parallel. What do you do when they're in parallel? You use this one, 1 divided by 2R plus 1 divided by R. So this calculation, this would give me 1 over R equivalent. But if I take the negative 1, the power of negative 1, which means basically flip the answer, do the calculation here, flip the answer, and it will give you R equivalent total. So this -1 here doesn't mean you can do 2R plus R. Don't do that, it will be wrong. So first you have to do the calculation here and then flip. So as you may remember, 2 divided by 3, for example, to the power of -1 is 3 divided by 2. But again, you have to first do the calculation inside. Okay, let's talk about short circuit now. Current prefers to go through a line rather than, so basically a wire without any resistance, rather than resistors connected in parallel. So if you have it set up like this, so the current would come here. So there's a way for current to go through this wire where there's no resistance, and there's also another way, this second path, third path. But if there's zero resistance, then the current would not prefer to go from resistance. It would just directly go from the wire because there's no resistance here. So in that case, no current flows parallel to the short circuit line. This is the short circuit line. So in this case, no current flows here on this one and on this one. So basically, this part of the circuit it gets shorted by this wire. So this wire without any resistance has no resistance, so it shorts the resistors R2 and R3. All current flows here on this wire since here there's no resistance. Of course, when you design a circuit, you don't make a short circuit like this. There's no point in making it. But what happens is usually if some of the wires are loose, or if, let's say, when you spill coffee or any other liquid on your laptop keyboard, what happens is those liquids, they can make connections because they include some minerals or sugar or maybe other, salt. So the liquid is conducting, so it actually connects different parts of the circuit, so it creates a short circuit. Or sometimes a loose cable within a machine or electronic device, if it touches at wrong points, so it may create a short circuit. So that creates that's an undesirable effect. Of course, you don't design it like this, and it makes the circuit useless, basically. So this is called shorting. Okay, let's do some examples with the circuits. Now we have a mixed connection here. As you can see, this 2 and 4, they are in series. And this 2 is in parallel with these 2 together, not individually. And all of these guys, these 3, they are all together, they're in parallel with this one. Sorry, they are parallel, they're in series with 2.5. So what I mean here is this 2, 2, and 4, they are not in series nor in parallel with this 2.5. But if you consider all of them, if you replace all of them with just one single resistor, that equivalent resistor will be in series with this 2.5 ohms. Okay, so now we want to find the voltage and the current on each resistor. How do we start? Well, the first thing we have to do is, now this battery is 24, but we cannot really say this is 24. The reason is there is another resistor here. So this battery 24 and this 2 ohms, they are not in parallel. So the only thing that I can do is, and I have to do is, find the equivalent resistance first, and then use that equivalent resistance to calculate the current here, and then go from that point. So let's start. So the first thing that you would do is you would start from here because they're in series. you would calculate the equivalent resistance, which is 6 ohms. So this makes this part of the circuit, so you have 2 ohms, this one, and now it's connected in parallel to this 6 ohm. Now what happens if you have 2 and 6? So this 2 and 6, while they're in parallel, then you would use this formula, 1/2, 1/6 to the power -1. It would give you the equivalent resistance here. So let's do that. If you do 1/6 and 1/2, and if you calculate this, so R in this, within this green circle, so for these 3 resistors, R equivalent is 1.5 ohms. Now that one, so our circuit is now like this, 24 volts. So here we have this 2.5 ohms, and it's connected to this 1.5 ohms. Now here we can calculate again the equivalent resistance. So because these are in series, 2.5 plus 1.5, it will make 4 ohms. So this is the total equivalent resistance. So here's the reduced circuit. So these two make 4. The voltage is 24. If you divide 24 by 4, you will find the current is 6 amperes. So again, that 6 is not necessarily going through each of these. That 6 is this, it's 6 amperes is the current that comes out or goes into this battery. So here we have 6 amperes. Okay, so let's put that 6 amperes that we found on here. So again, 6 comes out from the battery, and all of these points we have 6 amperes of current, and also it goes into the battery, and at all of these points we have 6 amperes. So 6 amperes, 6 amperes. Now at this point, though, it will split into 2. So these points are not 6. So these points are not 6. They will combine to give you 6, but not yet. So at these points, it's a different value. So, but at this point here, you can find the voltage, because through this resistor, we know the current and we know the resistance. If you just multiply these two, it will give you the voltage. So 6 times 2.5 gives you 15 volts. So here we have 15 volts. Okay, so if we have 16 volts here, and if we have 24 volts here, so remember this 15, it's a resistor, it's not a battery. It uses some of the voltage that this battery creates. So 24, here 24, here 15. So if you consider the voltage from this point to this point, it will be 24 minus 15, which is 9 volts. So here we have the voltage difference is 9 volts. So this creates 24, but this resistor eats up 15 volts of it. So what's left is, between these points, what's left is 9 volts. Now, next, use that potential at parallel. Use the observation that we talked about, which is potential at parallel circuit elements are the same. Now, if here we have 9 volts, which is these points, then this 9 volts, it's parallel to this resistor. So then there's going to be 9 volts on this resistor, and also 9 volts here together. So if there's 9 volts here, and if the resistance is 2, so 9 divided by 2, it will give you the current here as 4.5. Now, if the current is 4.5, if it goes here, remember the 6 split it into 2, so 4.5 goes down, then what's left here is 1.5 amperes. Now, so that 1.5 is the same. Remember, if there's no splitting in the wires, the current doesn't change. 1.5 amperes. Here, 4.5 comes down. And if you add them up, they will combine at this junction to give you, again, 6 amperes. Now, here you know the current and also the resistances. Then you can multiply them to find the voltage. So 2 times 1.5, here you have 3 volts. Again, 1.5 times 4 ohms, so it makes 6 volts. When you add this up, these two, it makes 9 volts, and indeed that's 9 volts that we already found it before, because we said here it would be 9 volts, so 9 volts on this resistor. And because these two are parallel to this one, so the total of these two should make 9 volts as well. So these are the currents, and if you multiply them by the resistors, you also get the voltages. So there may be different ways to solve the same circuit problem. So to develop your own skills, you have to solve a lot of problems on these circuits, different problems, so that you can you can get used to solving these problems. Okay, here's another example. The light bulbs in the circuits below are identical with the same resistance. So we have this one, R, they're connected in series, and we have also the ones that are connected in parallel, but the resistances are the same. Which circuit produces more light? So they're connected to the same battery. Okay, the battery is the same. The light bulbs, their resistances are the same. Okay, the only difference is the connection. And the question is, which circuit produces more power? So brightness of a light bulb is related to its power. So when we talk about brightness, the hint says here, we have to look at the power that's consumed on that light bulb or the resistor. You can think of light bulbs as the resistors. So you don't look at voltage, you don't look at the current on that resistor, but you look at the power. So find the total power for each circuit and then compare. So the brightness is related to power. Brightness is related to power. And remember, there are different ways to write power. It could be I times V, or it could be V squared divided by R, or we can also write it as I squared R. So you can use either one. Now in the series circuit, so we have two R's, they're connected in series. So if you want the equivalent resistance, it will be just 2R. And if you want to calculate the power produced by these two, you would do V squared divided by R equivalent. V is the battery, it's coming from the battery, V, divided by 2R. So it'll be V squared divided by 2R. But in the parallel connection, the equivalent resistor is R divided by 2. Why? Because you have to do 1 over R plus 1 over R to the power of -1. So this makes 2 over R. If you flip it, it will be R divided by 2. Now again, the same V, I keep the same V here. So in the denominator, in this case, it will be R divided by 2. Now put this 2 in the numerator now. It will be 2v squared divided by r. Now if you compare these two, this one is obviously greater. So the parallel circuit, it produces more power, or these two bulbs, when they're connected in parallel, they consume more power. So what it means is the second circuit, the parallel circuit, it will create more light, or it will be more bright. So the parallel circuit produces more light. So in this problem, we were interested in the total brightness of both light bulbs, but in general, if you have a circuit, maybe you can also have circuits like this. So instead of light bulbs, I will draw just resistors. So for example, you can have a circuit like this, and these could be light bulbs if you want. And the question could be, which one is the most bright, for example? So for these questions, as we mentioned here, what you have to calculate is not the current itself only, not only the voltage, but you have to calculate the power for each one, and you will compare whichever has the highest power. That means that light bulb is consuming the most energy, which means it's the most bright one. Okay, now section 5 of this chapter is about Kirchhoff's rules, or Kirchhoff rules, depending on, so in German, it's Kirchhoff's. So if you look at this circuit, now we have two batteries and a couple of resistors. So in this case, in this circuit, we cannot find R equivalent because of the way the batteries are connected. See, we cannot isolate in this case. For example, if you have just one battery, let's forget about this. If this was just a straight wire, then we could isolate the resistors, and we were able to find the equivalent resistance here. But if you have another battery here, now we are not able to calculate equivalent resistance, right? Because this one and this one is neither parallel nor in series. This one and this one is neither parallel nor in series. So we cannot really do anything here with the techniques that we learned so far. So we need another technique here, especially if you have more than one batteries, to be able to calculate the currents and the voltages at all circuit elements. Now, those rules to be able to calculate the voltages and the currents, those rules are called Kirchhoff's rules. So there are two of them. One of them is the junction rule. We already learned this, but it's also part of the Kirchhoff's rules. At all junctions, junction means two or more cable meet at the same, or wire meet at the same point. So here is the junction, and also this point B is also junction. The total current at junctions is going in is equal to total current going out. So the total current that goes in junction A is I1. The total current that goes out from junction A is I2 plus I3. So we have to write I1 equals I2 plus I3. Now the next rule is the loop rule. As you move in the loop direction along the circuit, so we are going to choose a loop. So let's say this loop in this part of the circuit. Now here's the rules. If you run into the negative end of the battery or a capacitor, it contributes as plus epsilon. So we will write down an equation like this. So let's say you move along the loop in the clockwise direction. So you run into a battery, and if you run into its negative end, indeed that's the case here. So you write the battery voltage as epsilon, not negative epsilon, but as positive epsilon, which is the case here. The second rule is if you run into a resistor and if the current, so there are two conditions, they should be satisfied. So you run into a resistor, let's say you go this way and you run into a resistor here. So we are going in the direction of the loop here. So we run into the resistor, and if the current is the same as the loop direction, let's see in this circuit here, on this resistor, the current is down and the loop direction is down also, so they're in the same direction, then the voltage from this resistor contributes as negative I times R. So of course we have the current I3, so I have to write negative I3 times R. R is the resistance of this resistor. And I continue here, I run into another resistor, is the current and the loop direction. Loop direction is the direction that I walk. So in this case, the loop direction is clockwise. The loop direction and the current, they're in the same direction, then it contributes negative sign. So it will be I1 times R, which is here. Now, after you write everything, all the circuit elements in the loop, then you equate them to 0. So from here, you get a relation as epsilon equals I3 times R plus I1 times R. So the other option is, so in this case, we chose a loop to be in clockwise direction. Let's choose another loop. Now that's in counterclockwise direction. Let's go in counterclockwise direction. Now, so let's say I started, it doesn't matter where you start, but I will start with the battery. So I will go in the loop direction. So I run into the battery, but I run into its positive end, not the negative end. So if I run into the positive end of the battery, then it will contribute as negative epsilon. Here's negative epsilon. Okay, so I handle the battery, so I run in the same direction as the loop, counterclockwise. Now I run into a resistor. So the loop direction, it's the direction that I walk on the wire, and the current direction, they are opposite. If they were the same, they would contribute negative, but if they're opposite, then they will contribute positive I1R, which is here. And again, I continue, and then now I come here. Again, the loop direction and the current direction, they're in opposite directions. So if they were in the same direction, it will contribute as negative. But since they are in the opposite directions, the contribution will be positive. So, and it will be I3 times R. So as if you compare these, if you, let's say, multiply this equation with a negative sign, so this will be negative, positive, positive. I can do that and it will not change anything. And I end up with the equation here. So these equations are actually exactly the same equations, which tells us that it doesn't matter which loop direction you choose, you will get the same equation. Yes, the rules change, so the negatives and positives, they change, but at the end of the day, you will get the same equation. So it's up to you to choose which way you go, you want to go in the circuit. So basically, you choose the loop direction, it's up to you. So these are the Kirchhoff's rules that we will use for the rest of the slides to analyze circuits, especially when they have more than one battery. If there's just one battery, as we did in the previous slides, you don't have to apply these rules. The loop, so basically writing down the equation for the loop. If you have just one battery, you can just calculate the equivalent resistance easily. But if you have 2 or more batteries, then there's only one option, which is using Kirchhoff's rules. So for a given circuit, there are many possible loops. For example, in the previous slide, we considered the loop here, either clockwise or anti-clockwise. But there are other possible loops for that circuit. For example, you can do a loop here in this part of the circuit. And the other option is you can also do a loop through these points. So if you have a circuit like this, then there are 3 possible loops. One is here, the other is here, and the third one is here. So from the second loop, let's consider this loop, loop 2. So if we try to apply Kirchhoff's rules, let's try to do that. So let's start this point with from this point. So there's this I2 coming in here in this direction. So it will go through this resistor in the down direction. So this will be I2. So the loop here drawn is clockwise. So let's walk down on this wire. So this is the loop direction. So you run into this resistor. Now the question that you have to ask yourself is the current on that resistor is in the same direction of the loop, or are they in opposite directions? Well, in this case, we go down this way, so the loop, so we will go in clockwise. And the current is down here, so the loop direction and the current, they are the same. So when they are the same, remember, we get a negative sign. So it will be negative I2 times R. And so we go in this direction. As you see, there's really nothing here, so we don't write anything. Then you run into the second resistor. And again, you ask the same question, is the loop direction, which is here in the up direction, and the current, which is down in the down direction here, are they the same? If they're the same, you put a negative sign, but because they are now opposite, you use a positive sign. So in this case, it will be I3 times R. And then you continue and you go back to the starting point. So that's it. So there are just 2 circuit elements. So you just write those 2 and then equate it to 0. Because there's no battery in this loop, so you don't write any epsilon. You can go counterclockwise if you want, and you will get the same equation, except this will be positive, this will be negative. But algebraically, those are the same equations, because if you multiply one of them with the negative sign, you will get the other one. So that again tells us that we can choose the loop direction as clockwise or counterclockwise. It's up to us. And let's do the large loop here. So we will not stop by the middle, the resistor in the middle here. We will only go outside. So let's start with this battery. So let's start with this point. So we will go clockwise again. But again, you can go counterclockwise as well, no problem. So we will go this way. So we first run into the battery. We run into its negative pole. Now look at the rule. So here, if you run into the negative pole, negative end of the battery or a capacitor, it contributes as positive. So this will contribute as positive epsilon. Then, so we come here, and then, so the loop direction is now this way. And the current is I2. It passes in this direction through the resistor. So the loop direction and the current direction are the same. And when they are the same, then we use a negative sign here. So it will be I2 times R. And then we come here, Notice that we don't go in on this resistor, so we come here. So the loop direction and the current direction, again, they're the same. So this will also contribute as with a negative sign. So you will write I1 times R, and then after that, you go back to the starting point. So you equate it to 0. So when we talk about loops, you have to make a loop a closed loop. So you cannot go this way and then go this way. So it would not be a loop. So it should be a closed loop. Now use equations from loop 1, 2, 3, and the junction equation to find the current I1, I2, and I3. So this is equation, second equation. This is third equation. And let's go back. This was the equation, the first equation. So we have 3 equations from the loops, and we also have this equation, right? The junction rule, which is here. So we actually have 4 equations, and we can use them to solve for I1, I2, and I3. And here is the summary of the loop rules. And so if you look at here, so let's say this is the loop direction. So loop direction is, think of it as the direction that you walk on the circuit. So in here, you would first run into the negative pole, which would contribute positive epsilon. And when you come here, there's a resistor, and the loop direction here, as shown, and the current direction, they are the same. They're in the same direction. So this would contribute a negative sign. Now, if you, instead of minus plus, if you have, let's say, plus minus, and if you walk on this wire, first you would run into positive end of the battery. So that would contribute a negative sign. Okay, and let's discuss what happens if the current and the loop direction if they are opposite. For example, here, if the current is to the left, but the loop direction is to the right, then that would contribute a positive sign. So these 4 situations they're basically all possibilities that you could run into, but it's enough to memorize only this one, because you can get the other ones from this one. For example, if you flip the poles of the battery, then instead of epsilon, you would get negative epsilon. As you can see, they're plus minus, plus minus. Or if you flip the direction of current, which is this case, and this case, you would get a positive sign in front of the current term. So if you just learn the first one, it's easier to derive the other ones. And finally, so if you look at these terms, these are all voltage terms, right? So when we write the loop equation, we are actually writing the voltages. So for example, the first one is the voltage difference between these points. And there's no voltage difference between this, the points on the same wire. So, and the second term, I2 times R, remember I2 is here. It's the voltage difference between these points. And the third term, I times R, remember this is actually V equals IR, Ohm's law. Again, this is the voltage, and this is the voltage difference between this point and this point. And because we go back to the starting point, the voltage difference between this point and when you do a loop and this point, which is the same point, should be 0. Because the voltage, there cannot be any voltage difference at the same point. And that's the meaning of this 0. So here's an example. So the question is, so you have the battery, you have the resistors, but the currents are not given. So the question here is calculate the currents I1, I2, and I3. So I1 is here, I2 is here, and I3 is passing through this resistor. So initially, we don't know the correct directions of the currents, okay? So maybe I3 is flowing this way, we don't know. So what do we do if we don't know the directions of the current? Well, what you have to do is you have to just choose the current directions arbitrarily. So you can choose them arbitrarily. In this problem, I chose I1 to be this direction, I2 to be this direction, and I3 to be down direction here. So before you solve, before you actually find those numbers, it's not easy to tell which direction they will be, but that's okay. You can just make a guess initially, or just you don't even have to make a guess. You can just choose arbitrarily some directions and also choose some loop directions arbitrarily again. So clockwise or counterclockwise, doesn't matter. And start doing your calculations. First, when you choose the currents like this, so I1 comes in and it breaks into, splits into I2 and I3. So from this, then I have to write I1 equals I2 plus I3. But if you choose the directions, let's say if you choose I2 to the left direction like this, then we would write I1 plus I2 equals I3. So in that case, it will be different. Anyway, so you choose the directions arbitrarily, it's up to you. And then for those directions, you write this equation, the junction rule. And for this junction, and for point B, it will be the same equation. So we have one equation at hand. Then we will use now we will write equations for these loops. Sometimes just one loop is fine. It's enough to solve the problem. Sometimes you have to do 2 loops, or sometimes even 3 loops. The third loop would be this large loop. But the maximum number of loops that you can write for this circuit, it's 3. If you have more complicated circuits, of course, you may be able to write more than 3 loops. Okay, let's continue. Now so we first have the junction rule. So in this case, I1 equals I2 plus I3. But don't memorize this, okay? This is valid for this problem. Again, if I choose, let's say, the current direction, I2, as to the left, then I would write I3 equals I1 plus I2. So it's different than this one. So don't memorize this form. It can be different. So, but the idea is at the junction, the currents that go in, which in this case, the current that goes in is just I1, it's equal to the currents that go out from that junction. This is the junction. The currents that go out is I2 and I3, so I1 equals I2 plus I3. Now let's go into the loops. So for loop 1, I'm going to start from, I like to start from the battery, but it doesn't have to be, you can start from anywhere. So we will go in this direction. So I run into the battery, it's negative pole. I first run into its negative pole. So when that happens, remember we use a positive sign. So this is going to be positive 15. And then I continue, so there's nothing here, just the wire. And I now come here, so there's a resistor. Now look at the direction of the current that I chose, down direction. And the loop direction is down. So when the current and the loop direction is the same, then it contributes with a negative sign as per the Kirchhoff's rule. So a negative sign. And I have to do 100 times I3, which is here. And then now this is done. I go back to this way. Now I run into another resistor. So it will be again 100 times I1 this time. And the loop direction and the current direction are the same. So there will be again a negative sign. So negative I1. I1. Notice that here we have I3 and here I1. So the currents on these resistors are different. So you have to be careful with the subscripts. You have to write the correct current. So after that point, since I go back to the initial point, so then that's time to equate this equation to 0. So we have one equation here. We got the second equation. Now let's get another equation from this time from loop 2. So loop 2 is also clockwise, chosen clockwise. Again, you can choose it to be counterclockwise as well. Let's start with, so we will start from here and go clockwise this direction. Now, so I go this direction, I run into a battery, but I run into its positive pole. So if that happens, remember, you get a negative sign. So -9. And I continue, I run into this resistor. So here I2 goes, so this is the direction of current. The current and the loop direction are the same, then there will be negative sign. So 100 times I2. And then I continue and try to complete the loop. So I run into this resistor now. Now the loop direction and the current direction, they are in opposite direction. So there will be a positive sign here. So the value will be I3 times 100. And because I go back to the initial position now, I have to equate it to 0. Now, let me rewrite the junction rule as I2 equals I1 minus I3. Now, if you look at loop 1 equation and loop 2 equations, we have I1, I3, and I2. So we have 3 variables here. So, but by using junction rule, we can actually reduce we can get rid of one of the variables. For example, we can get rid of I3, I2. Because here I3, I1, there's I3. So if I get rid of I2, if I write it in terms of I1 and I3, I would have 2 equations and 2 unknowns, I1 and I3. So to be able to do that, I will use junction rule. I will rewrite it as I2 equals I1 minus I3. The reason that I write it this way is because I want to get rid of this I2. So instead of I2, I will plug in this expression, which is I1 minus I3. Now this one, the second one, becomes -9 minus 100 I1 minus I3, this term, minus 100 I3. Sorry, this should be plus, so there's plus 100 I3. So this is actually the loop 2 equation. And from here, I can solve for I1. So put this on the other side, also this term 9, and then divided by 100. What you find is I1, you can write it in terms of I3. So we basically combined the junction rule and loop 2 equation to find this equation. Now plug I1 back to loop 1 equation. Now I1 is in terms of I3. Now, if you look at loop 1 equation, there are 2 variables, I3 and I1. But if I plug this in, this term, this expression here, into here, loop 1 equation will be only in terms of I3 because this only depends on I3. So now loop 1 equation becomes plus 15, -100 instead of I3, well, we will keep I3. So we have -100 I1, -100. So instead of I1, we will write this thing here. And it's equal to 0. Now, as you can see, this equation, loop 1 equation, is now it only depends on I3. So it's one equation, one unknown. You can solve for I3, and here is the solution. So turns out I3 is 0.08 amperes. Okay, so once you know I3, then you can now plug it here to solve for I1, and it's 0.07 amperes. Okay, now you know I3 and I1. If you know these two, then plug these two into the junction rule, which is the easiest equation here, to find I2. So I2 turns out to be negative 0.01 amperes. Now, what is this negative sign? What is the meaning of this negative sign? Okay, here's the explanation. Here, the negative sign of I2 indicates that our initial guess about the direction of I2 as clockwise was wrong. So we chose this direction. We assumed that I2 was flowing this way. Okay, that was so we chose it arbitrarily. And at the end, we found it to be negative. So what it means is we actually chose it wrong. So I2 is actually flowing counterclockwise. So what it means is the correct direction of I2 is actually in this direction. So I2 is flowing this direction. Here, I2 is flowing this direction. Okay, so at this point, you don't have to change, you don't have to redo the calculations. You don't have to. So the values are correct. Okay, you don't have to do the calculations. Again, the values are correct. The only thing that this negative sign just signals us that the correct direction of I2 is not the direction that we chose initially, but it's in the opposite direction. Well, other than that, the values are correct. So to summarize the solution, let's go back one slide. So we have a question. That question is usually, the loop direction is not shown. It's not given. The current directions are not given. Maybe let's draw it here. So the question will be like this. So 15 volts. And there's this 100 ohms of resistor. And another resistor here. This is 100 ohms. And we have another battery here. So this is 9 volts. And another resistor here. This is 100 ohms again. So the question will be only like this. So the loop directions will not be shown. The current directions will not be shown. So what do you do when you see a question like this? The first thing that you have to do, choose the current directions arbitrarily. So you have to choose current directions. In this one, we chose this and we named it I1. If you want, you can name it a different variable, no problem. For here, we chose I2, and that would be, so we chose this direction. And here, we chose down direction, and we called it I3. And for the loops, we chose them clockwise. But again, you can choose counterclockwise loops. These are clockwise. You can choose the directions of the currents initially in different directions. Doesn't matter. The final values will be always correct. But the only caution here is that if you find a negative value for a current, then know that the direction of the current for that part of the circuit is not correct. The direction should be in the opposite direction. But again, you don't redo the calculations. The values are correct. So for this circuit, we had to use the junction rule and the equation from loop 1 and the equation from loop 2. So these were enough for this question. For some questions, if there are more unknowns, then you may need to also use maybe another loop, which maybe in this case, it will be this loop as well. And sometimes even just for one loop may be enough. It depends on the question. Okay, we can also talk about potential difference between 2 points on the circuit like B to A. So you can have a circuit like this. Maybe the rest, so it's maybe part of the a larger circuit. Maybe there are other elements here. Maybe it's connected to a battery. Okay, but you don't have to know the rest. you can always calculate the potential difference between 2 points. So the potential difference between B and A, it will be current times resistance. Current is 0.25. Resistance is, now these are in series, so 6.2 plus 12. And if you do the multiplication, you find the potential difference to be, so the potential difference is 4.9 volts. But we can also use the loop rules to find the potential difference between B and A. Now, how do you use it? If you remember this rule here, this was the first, so there were 4 of them. This was the first, and I said if you remember the rule here, then you can derive the other ones. So by using, again, the loop rules, so from B to A, we will calculate the potential difference. Write starting point's potential as positive. So let's move, so you can move up to down or down to up, but let's move in the direction of the current so that we don't, we can use this, we can directly put a negative sign and write it IR. So we first start from this point. So we write this point's potential as positive. So write the starting point's potential as positive, and final point's potential as negative. So before coming to that, so we started from here, we wrote VB, and then so now we run into this resistor, the current and the loop direction. So let's say this is our loop direction. Loop direction and the current, they are in the same direction, so there will be a negative sign as per this rule. And we will write 6.2 times the current. And so now we are here. Now we will write the voltage for this resistor. So it will be, again, negative sign because the current now flows in this way. So 0.27 times 12 ohms. We write it here. And final point's potential as negative. So we will write the final point's potential as negative. So we will write negative VA. And then we will equate it to 0. So now if you think about VB minus VA, so VB minus VA, which is here, so, and take these two numbers on the other side as positive. So if you do the calculation, you will find it's 4.9 volts. So VB minus VA, it also, we can write it as delta V B minus A, which is the same number as we found here. Now, you may ask this question, when we did loops with the circuits, let's say we had a battery here, and then let's say we have a resistor here, let's say epsilon R, let's say this is the current direction, and let's say this is the loop direction. So we start at this point. So you may ask, we never wrote VB and VA. Okay, so let's see what happens if we write those points as well. Let's say this point is C. So let's write first, let's start from this point, VC. And so we go this way, loop direction, clockwise here. So we run into the battery, negative end. So we will write, it will contribute positive epsilon, as you can see here. If you first run into the negative pole of the battery, as you go through the wire in the loop direction, it contributes a positive sign. And then we would come here. So there's this resistor, so it will contribute as negative IR. And then we will come to that point. So you have to write the final point's potential as negative. So we will write as negative VC. And then equate it to 0. Now, these VCs, they cancel each other. So we get back to this thing, which we learned, which is what we learned before. So the reason that we don't write the initial and final positions potentials is because we get back to the starting point. So even if you write them, they will cancel each other at the end. So that's why in the previous examples, for example here, we did not write the initial positions potential here. We could write it, let's say that this is point C, so we can add VC here. And when we do the loop, we come back to that VC. So here we would add negative VC equals 0, but these would cancel each other. So when you do a loop, you don't have to write the potential of the initial and final position, which is the same. Initial and final position is the same on the loop, and that's why they cancel each other. But if you don't have a complete loop or only a section of the circuit like this, then in that case, you have to write the initial and the final points potentials. Okay, so here's an example. Point A is grounded. Grounded means it's this side. It means, so it's connected to the earth. So it means you have to take the potential of this point to be 0. So VA is 0, as you can see here. So find the potential at B and C by using point A. So we will find the potential at this point and at point C by using this, the fact that this point is set to 0 potential. Okay, so you can go from B to A in different ways. So for example, first let's go from A to B or B to A by going through the resistors 6.2 and 12. So let's start from A, and then we will go to B in this direction. So this will be our loop rule if you want. So this is the loop. So what was the rule? First, write the potential of the starting point as positive, which is here. And then we come here, so notice that I2 is now here going down. So this is I2. Loop direction is up, current is going down. They are opposite, so it should contribute as a positive sign. So the value will be 12 times I2, which is 0.27. Okay, so now we pass this resistor and come to the next one. The current direction and the loop direction, again, opposite. So we, again, have the positive sign, and the value will be 6.2 times 0.27 here. And then finally, we come to point B. Remember the rule. Let's go back. So write final points potential as negative. So that's the rule. So we will write the final point as VB. We will write it as negative here. And finally, we equate this equation to 0. Now, if you solve for VB, what you find is VA, and these two makes 4.9, and VA is 0 because it's grounded to the earth. So VA is 0. Then it turns out VB is 4.9 volts. Okay, so if VB is 4.9, then all of these points, so until the end of this resistor, also until this point, and also if you go this way, all of these points, the red dots, they will be at 4.9 volts. Okay, but if you, of course, if you pass the resistor, then it will be a different voltage. Now, if you look at here, then you may be wondering, how is it possible to have 4.9 volts here, even though the battery is 15 volts? Well, this 15 volts is not the voltage at the positive terminal. 15 volts is the voltage difference. This is actually delta V between the terminals. So it doesn't have to be, so this terminal, the positive terminal, doesn't have to be at 15 volts. So as you can see here in this example, it's at 4.9 volts. So now the negative terminal, then let's find the negative terminal. So if positive terminal is at 4.9 volts, then the difference between the negative terminal and the positive terminal should be 15. So this difference should be 15. Then that tells us this point should be at a negative value. So it should be at negative 10.1 volts. Now you can see that the difference between 4.9 and negative 10.1 is actually 15. You can do it here. For 4.9 minus 10.1 is 15. So the difference is now 15. So the bottom line here is so this value is the voltage difference between the terminals of the battery. It's not the voltage of the positive terminal. Okay, so this point is negative 10.1 volts, and also these points are at negative 10.1 volts. Now let's do the same exercise by using a different resistor. So we will try to find the potential at point B by using the fact that the potential at A is 0 because it's grounded. So we use this path in this calculation. Now let's use this path. So we will go from A to B over 0.7 ohm resistor. So we will go from A to B. So let's choose this to be the loop direction. Well, it's not a loop, it's path, let's say path direction. So again, you write the initial position's potential as positive, VA. And so you go this way, so you run into this resistor. Loop direction and the current direction are opposite, so you get a positive sign. 7.5 times 0.65 will be the value, the voltage on that resistor. And then after that, you come to point B. You write the final point's potential with a negative sign. And so here again, you can solve for VB. It will be VA times this multiplication makes 4.9. And VA is again, because it's grounded, it's 0. So VB again makes 4.9, just like in the previous trial. Now let's do this. Let's go from A to B over this resistor and the battery. So we should get the same number. So this is a good exercise because you get to use the Kirchhoff's rules, the loop rules. So now again, we start from VA, we write it as positive, and then here, so this is the direction that we will travel, path direction. Here, the path direction or the loop direction and the current, they are in the same direction, so it will contribute as a negative sign. 11 times the current, 0.92, and then so you move to here, this point, VC. Okay, so in this part, we are actually trying to find VC, not VB. So we are going from A to C. So we start from VA and V road. So we go this way, path direction. There's actually just one circuit element, which is here. And the final point is C. So you write it with negative sign because it's the final point. Now solve for VC, it will be VA minus 10.1. And because VA is 0, turns out that VC is negative 10.1. In fact, we had found this number because we had found the voltage here to be 4.9. And by knowing the voltage at the positive terminal and by knowing the delta V, 15 volts, the voltage difference between the terminals of the battery, we were able to find that this point should be at potential V negative 10.1 volts. And here we actually verified it by writing the loop rule for between points A and C. Okay, finally, what we are going to do is we will start from A and we will go over this resistor, and then we will go over also the battery to reach C. So we start from point A, we are going to write VA. The starting point comes with positive sign, and then we go over this resistor, so it will be 7.5 times 0.65. Now the loop or path direction and the current direction, they're opposite. Then that would by now you already know it should contribute a positive sign. So 7.5 times 0.65, it's here. Now after that, after the resistor, there's nothing here and there's the battery here. Now what happens as you walk? What happens if you first see the positive end of the terminal? Now look at here. If you first run into the positive end of the terminal, it contributes a negative sign with a negative sign. So it will be negative 15, which is here. And this is the final point, and you write it with negative sign. So it will be negative VC. Again, solve for VC. VA minus 10.1. VA is 0 because it's grounded. That's the definition of grounding. And then from here, you find, again, VC is equal to negative 10.1 volts. So it's a good idea to do all of these exercises on your own to get used to it, to get the skills of problem solving in this subject. Okay, now let's move to capacitors. Now we connected resistors in parallel and in series. Now we will do the same with the capacitors. If you remember from chapter 20, the amount of charge on the capacitor would be equal to capacitance, which is a value of the capacitor. Maybe, so it depends on the area of the capacitor, the distance between the plates, and so also the thing that the dielectric, if you have kappa inside, so it would depend on those values. So C times the voltage applied between the ends, the terminals of the capacitor. So that would give you the charge on the capacitor. So connecting capacitors in series and parallel, let's start with the parallels. If you have parallel capacitors like these, then the equivalent capacitance here would be C1 plus C2 plus C3. And again, the rule that the voltage is the same on all parallel circuit elements is valid. So if the voltage is the same, so we have epsilon here, then the voltage here is epsilon, here it's epsilon, and here it's epsilon. So then you can apply this formula on each capacitor. So for this one, it will be, so basically voltage equals Q divided by C. So for the first one, it will be Q1 divided by C1. For the second one, epsilon is equal to Q2 divided by C2. And for the third one, epsilon is equal to Q3 divided by C3. But notice that they are the same epsilons, the voltage of the battery. Why? Because the voltage is the same on all parallel circuit elements. And if you want to find the total Q, what you can do is you can find the equivalent capacitance. And then from this equation, so you would write Q equals C equivalent times the voltage. So this would give you the total charge on this capacitor. Now, what happens if you connect them in series? So if you connect them in series, as you can see here, the charges are the same. So just like the currents are the same on a cable that's not interrupted, just like the current is the same, here the charges are the same. So if this is plus Q, this is negative Q. This is plus Q because it's connected to the positive terminal, and the other side should be negative Q. And if it's negative Q, then this part should be plus Q, negative Q, plus Q, negative Q. So here the signs are alternating, negative plus, but here with the battery they have the same signs. So negative sign here, and negative Q here. So if you connect capacitors like this, the equivalent capacitance will be calculated by this formula. Now, if you look at these formulas, they look like the formulas that we use for resistors, but we used so here, if you connect in series, the capacitors in series, you get this formula, but we use this formula when for the resistors when they are connected in parallel. And we use this formula for resistors, a similar formula, when they are connected not in parallel, but in series. So in terms of formulas, the resistors and the capacitors, they are just opposite to each other. And finally here, charge is the same on all capacitors connected in series. This is, as I said, just like, remember, the current will be the same in all circuit elements when they're connected in series. So, and current, remember, current is related to charge. It's the amount of charge that passes through a point on a wire per time. So, and for this case, again, you can apply this formula, Q equals CV, on each one. So, but for this case, what we have is the voltages are not the same, but the charges are the same. So here, if you write Q, that equation, Q equals C1 V1. Here it will be Q equals C2 V2. So V1 is the voltage here. V2 is the voltage on this capacitor. And here we will write Q again equals C3 V3. These Qs are the same. The values of these Qs are the same. And when you apply this formula, so this Q is the amount of charge on one plate of the capacitor. So you see in this, so when you have a capacitor, it's something like this. So positive charges collected here, negative charges collected here. So this is a charge capacitor. When you charge a capacitor, it becomes like this, and then you can connect it if you want to let's say a resistor or a LED to light it up. But so the charges, so let's say plus Q, the total charge, and here the total charge is negative Q. When you apply this formula, Q equals C times V. So V would be the voltage that you connect to charge it, to have these charges on the plates. So when you apply this formula, you don't write here 2Q. So you are just writing the charge in one plate of the capacitor. So it's just Q. Okay, find the equivalent capacitance here. First, you notice that this part, they are in series. The reason that we start from this part, the reason for that is that's the only thing that we can do, right? Because these two are neither parallel nor in series, because there's this cable that goes this way. They cannot be series or parallel. They're not parallel because there's another one connected to this one. They're not connected directly. Also, this one and this one, they are not parallel because there's another C that interrupts the cable, the wire. So I cannot start with this one. So I have to start with these two. They are in series. What do we do when they're in series? We use this formula, C equivalent equals 1 over C plus 1 over C. So this is 2 over C. If you flip it to find C equivalent, it's C divided by 2. So this part is C divided by 2. So it's C divided by 2. And now we can combine it with this blue color C. So because what we have here is now we have this circuit. So here we have this blue color C. And then the rest here is now, it's C divided by 2, and it's now parallel to this circuit, to this capacitor. So when you have two capacitors in parallel, then you just add them up. So C plus C divided by 2, it's 3C divided by 2. So this is the equivalent capacitance when measured between these two terminals. Okay, let's take a look at this example. Find equivalent capacitance and also the charge, voltage, and energy on each capacitor. The voltage drop on 20 microfarad capacitor is 12 volts since it's parallel to the battery. So this battery here, 12 volts, it's parallel to this one. So that here it should be 12 volts. So from this information, I can use Q equals CV. So I know C, 20 microfarad, 10 to the negative 6 is micro, multiplied by the voltage, and you find the charge on that capacitor. So this is the charge on this capacitor. Now 10 microfarad and 5 microfarad, these two are connected in series. So remember, when they're connected in series, here they have the same charge. Charge is the same on all capacitors connected in series. So they're connected in series. They have the same charge on them. Let's call it Q. Let's say this has charge Q and this has charge Q. Since they are in series and together they are parallel to the battery, the voltages on them, let's call them V10 and V5. So the voltage here is, let's call it V10, here V subscript 5. So they will sum up to 12, right? Because they're parallel to this 12 volts together. So V10 plus V5 should be 12. Now let's remember the formula. Q equals CV and V equals Q divided by C. So instead of V's, now I will write Q divided by C. So here, Q divided by, it's 10 microfarad, so 10 times 10 to the negative 6, plus for this one, again, Q divided by C, its capacitance is 5 microfarad. It's equal to 12. Now notice that this is important. I am writing the same, using the same variable. I don't use Q1 and Q2 because as we mentioned here, because these are connected in series, they have to have the same charge. Okay, so we have one equation here. The only unknown is Q, so you can solve for Q, which is 4 times 10 to the negative 5 coulomb. So now we know how much charge on each one, how much charge there is on each capacitor. Okay, so if you know Q, so you know Q, you know their capacitance values, so then you can find the voltages. So basically you can find V10 and V5. And to do that, so it's basically Q divided by, you apply that for this formula. Now we know Q values, the charges, so plug in Q values, you know the C capacitance values, and it turns out one of them is 4 volts and the other one is at 8 volts. And if you add these up, so 4.4 plus 8 gives you 12 volts, which makes sense because this should be 12 volts just because the battery here is parallel to them and the battery voltage is 12. Okay, so now we can also calculate the equivalent capacitance. So first I have to start here because these two are in series. These two are neither in series, neither nor in parallel. These two are neither in series nor parallel. So I cannot really use this one first. What I have to do is I have to find the equivalent capacitance first here. And because these are in series, I have to use the 1 over C formula here. So I call this part C1, and C1 turns out to be 10 divided by 3 microfarad. When you use this formula, so we are basically using this formula, 1 over 10 plus 1 over 5. So you don't have to convert these, so these are in microfarad, but you don't have to convert them into farad. If you use just this formula, if you don't convert them, the result will be again in microfarad, which is fine. Now to find the equivalent capacitance of the whole circuit here, this part of the circuit, now we have this capacitance here, which is now we calculated to be 10 divided by 3 microfarad. Now this is connected to the other capacitor here, which is 20 microfarad. As you can see, these are in parallel, and when the capacitors are parallel, you just add the capacitance values, which turns out to be 23.3 microfarad. So the capacitance, equivalent capacitance here is 23.3 microfarad. Okay, now let's calculate the energy stored in these capacitors. This goes back to chapter 20. The energy stored in the capacitors is CV squared divided by 2. Or you can use QV divided by 2, or you can use Q squared divided by 2C. So you can go from one equation to another by using Q equals CV. Now, here in this calculation, I will use the first form. So for each one, you write the C values, and then the voltages on each one. So on this one, the voltage was 12 because it's parallel to this one. And for the other ones, the top one was 4 volts, the bottom one was 8 volts. So this is 4 volts, this is at 8 volts. So you take the square of the voltages because in the formula there's square, and finally divide them by 2, and you will find the energy stored in each capacitor. And if you want to find the total energy stored here in those capacitors, then you would basically add these values, which gives you 168 times 10 to the negative 5 joules. Now there's a second way to calculate the total energy, which is by using not individually all of these capacitors individually, but by using the equivalent capacitance. So think of this circuit as there's just one capacitance instead of 3, and that the value is the equivalent capacitance, which is here. You can also do that. So the C value is this one. And the voltage here, then, well, this equivalent capacitance is connected to 12 volts. So you would use 12 squared and also divided by 2, and you will get the same value. So this is the energy, the total energy stored in these capacitors. Okay, so in this example, we have 2 capacitors again. So initially they are charged. So this has some charge, and this also has, the second one also has half of the charge that the C1 has. So this one has 120 microcoulomb, and the second one has 60 microcoulomb of charge. The question is, and see that the switch is open, so they're not connected yet. The question is, what will be the final charges of the capacitors? Let's call them Q1 final and Q2 final after we close the switch. Now, first of all, the total charge is conserved. You cannot create or destroy charge because charges they're coming from electrons, so you cannot destroy or create electrons, so it will be conserved. And it will be shared by the capacitors according to this formula. So the initial total charge is 120 plus 60, so it's 180, 10 to the negative 6 coulomb. And that initial charge will be equal to the final charge because charge is conserved. Now also the voltages on each capacitor will be the same after we close the switch, since they become in parallel when the switch is closed. So when you close the switch, and if it's a full circle like that, then if you imagine that you measure the voltage here between these 2 points. So in this case, these two are in parallel. And so you measure the voltage. So let's say V1, V2, and those V1 and V2, they should be the same. So V1 equals V2. So V1 is the voltage on the first capacitor, and V2 is the voltage on the second one. So, but we can use this formula, V equals Q divided by C, which is actually this formula. Now, let's write this equation in terms of charges. So in the final situation, so the first V1 will be Q1 final divided by C1, and V2 will be Q2 final divided by C2. And let's here solve for Q1 final. So Q1 final will be Q2 final times C1 divided by C2. So C1 here is in the denominator, so we send it back to the other side. So now it's in the numerator, so you get this relation. So we know C1 and C2, so they're not unknowns, they're known, but the unknowns are Q1 final and Q2 final. So we have 2 unknowns, and we actually have 2 equations. Now, one equation is here between Q1 final and Q2 final. The second equation is here between Q1 final and Q2 final. Now solve these equations simultaneously, which means if you want, so instead of Q1 final here, plug in this value here. So this first equation will be only in terms of Q2 final, and solve for Q2 final. Once you find Q2 final, you can plug in back in here or in here to find Q1 final. So by this way, you can find Q1 final and Q2 final. And if you do the calculation, it turns out Q1 final is 144 microcoulomb and Q2 final is 36 microcoulomb. The initial values were 120 and 60. And the final values are 144 for this one, 144, and for this one, 36. Now look at the initial total, 180. Look at the final total, it's still 180, because the reason for that is the total charge is conserved. Now we move to RC circuits. So RC circuits are the circuits where you connect the resistor, a resistor and a capacitor. So these are called RC circuits, and they have they show the current and the charge becomes time dependent, and their functional form becomes an exponential. So before we move to RC circuits, let me show you the exponential function. So here we plot the function with respect to time. So the x-axis is the time. If you have a function like this, 10 times exponential negative time divided by some number, it will give you, so exponential decay, because you have a negative sign here. So let's say f0 is at time equals 0. So exponential to negative 0, which is 1, because e to the power of 0, it's always 1, positive or negative, doesn't matter. So it's always 1. So you will get 10 here. Now, if you plug in numbers after when t equals t, let's say f t equals, let's say 5, or let's make it 9. So what do you get? 10 times exponential negative 9 divided by 9. So this is like 10 times exponential to the power of negative 1. So it's like 1 over e. And e is a number about 2.7. And this becomes something like approximately, I think, 3.5. So it went down from 10 to approximately 3.5. And as time passes by, if you let's say instead of 9, if you put 100 or 1000, then it goes to 0, as you can see here. It's a decreasing function, and that decrease happens here because of this negative sign. If you have a positive sign here, then you would get an increase. Now let's also discuss the role of this number in the exponent. So this number in the exponent. So if you compare these two functions and their plots, their amplitude is the same, 10, and the exponential function is the same, except there is the difference here. It has 9, here it has 2. Now, as you can see, if this number is small, then the decay happens more quickly. If this number is large, in this case 9, the decays takes more time. So that's the meaning of that number. In the following slide, instead of these numbers, we will have tau, and it will be equal to the resistance times the capacitance in the circuit. And this tau will determine how fast the charging will happen, or how quickly or how slow the charging or discharging a capacitor will happen. So the formula that we will have a couple of formulas for charging and discharging, and they will be in the form of exponential negative time divided by tau. So this tau, this is a constant. It's a constant. It's the resistance value in ohms and capacitance value in farad. But this t is time dependent, so our equations will be time dependent. Okay, so let's say now we have an RC circuit. Here's an RC circuit here. There's the battery, there's R, and there's C. When we close the switch, let's say the switch was initially open and capacitance is empty, it's not charged, but we close that switch so the capacitor starts to get charged. When we close the switch, it takes time to charge the capacitor. Time constant, tau, is R times C. So basically this R value times this C value. It determines how fast it will be charged. As the capacitor is getting charged, let's think about charging now. The current in the circuit is decreasing since the voltage on the capacitors is increasing and it's working against the battery. Now, if you look at the polarity of the capacitor, the side of the capacitor that's connected to the positive terminal of the battery, it will be positive, and the other side will be negative. Now, as the capacitor is getting charged, it becomes like a battery, which is like this. So positive and negative. So, and if you think about the circuit, this capacitor positive end is connected to the positive end of the battery, or let's put it this way. This end of the capacitor is getting positively charged, and the reason for that is this end is connected to the positive terminals of the battery. But as this capacitor is charging, it's getting charged, the voltage on the capacitor is increasing. And if you think of the capacitor as a battery, it's connected to this battery as it's getting charged. Its polarity is against this battery. So if you maybe draw it this way, so this is the epsilon. This is our real battery here. And so there's this resistance here. And the capacitor, so it's like a battery. You can think of it as a battery. It's connected like this. This is the capacitor. So you can see that the capacitor and the battery polarities they are working against each other. So this battery is trying to create current in this way, and this capacitor, as it's charged, after it's getting charged, now it will have some voltage on it. Why? Because when there's charge, it creates voltage, and it will try to create current in the opposite direction. So this capacitor, as it gets charged, it starts working against the battery in the circuit. That's why the current in the circuit is decreasing as the capacitor is getting charged. And that's plotted here. So when initially the capacitor is empty, so it doesn't act as a battery. Initially, you can think of we have only the battery and the resistor. And the current here would be use Ohm's law. So the current would be epsilon divided by R. So initially, current is epsilon divided by R at time equals 0. So initially, the current is maximum. But as the capacitor is getting charged, it builds up voltage, which is in the opposite direction to this battery. So you can think of it as it creates, so this is the current coming from the battery. And the capacitor creates its own current in the opposite direction. So the total current in the circuit is decreasing. And in fact, when the battery is completely full, completely charged, let's say if you have 9 volts, this will also be 9 volts, and the polarity is positive, is connected to positive, so the current will go to 0. So current at time equals 0 is epsilon divided by R, comes from this epsilon divided by R, because initially there's no voltage on the capacitor. It acts like a straight wire. But then as time goes on, in fact, if time goes to infinity, the current goes to 0. The exponential, so this is again the exponential function that we just talked about in the previous slide. So instead of now 2 or 9, we have the tau. here in the exponent. And here, this is the initial value. So this is I0, which means current at time equals 0. Remember, this was the decaying function, so it starts from the maximum and it goes down as the time passes. So this is the current on the circuit. Now, what about the charge on the capacitor? Initially, it was not charged. We close the switch. So now we started getting some current, which would charge this capacitor. So initially, it started the charge. Now we're talking about charge. It starts from 0, the charge is 0, and then it will increase, and when it's completely full, then it will be the maximum charge on this capacitor. Remember, this is actually Q equals CV. Here, voltage is epsilon. It's the electromotive force or the voltage of the battery. So the maximum charge will be C times epsilon. And this is again an exponential function. But the form here will be 1 minus exponent, because at time equals 0, so this will give me exponential negative 0 divided by tau, which is exponential negative 0, which is exponential, which is 1. So this term is 1 at time equals 0, and this term is 1. So 1 minus 1, it gives you 0, which is correct. At time equals 0, you get 0 charge. And as time passes by, the second term, its effect is getting smaller and smaller. And 1 minus smaller number, it becomes larger and larger, as you see in this plot. So this is the charge, the function of the charge, time dependent of that capacitor. So the charge is increasing with time. The current in the circuit and the charging stop when the voltage on the capacitor becomes epsilon. So as time goes to infinity, the charge on the capacitor becomes Q equals CV. So instead of V here, we have epsilon. And this is the time-dependent formula for the charge. In DC circuits, DC means a direct current, which means constant voltage source, which is when you have a battery or a capacitor. Completely charged capacitor act as a broken circuit. So you close the switch and then it charges after, so the battery charges the capacitor. And when the capacitor is completely charged, then it stops letting the current pass. Because remember, it produces its own current exactly in the opposite direction to the current that's created by the battery. So the total current goes to 0. So it doesn't allow the current to pass when it's completely full. So it acts as a broken circuit. So this circuit, when the battery is completely charged, it becomes something like this. So broken circuit. So the current stops flowing when it's fully charged. So we talked about charging a battery. Let's talk about discharging it. How do you discharge a battery? Well, you basically connect it to a resistor. Now this battery, it will just act like a battery like this capacitor. So it will create current in this direction because this part is positive. This part is negative. So the energy of the capacitor will go into to heat or light within. So this resistor will use up that energy and turn some of it to heat or light. So when the energy of the capacitor is getting used, then the charge on the capacitor goes down. So when a charged capacitor connected to a resistor, it starts discharging. The current decreases just as in charging. Now the current, again, it decreases. So it starts at a maximum value. So let's say it has some voltage, V, So it starts from V divided by R. This time voltage is not coming from the battery, but it's coming from the capacitance. And so this is current. So the current starts from V divided by R, and it will be going down like this. But the charge and also the charge, it will also be decreasing. In the previous case, the charge was increasing because we were charging it. Now we are using up the energy or the charge. So now this equation here, this formula, it shows that the charge, so there's now exponential. So the charge Q will be going down. It will start with initial charge, whatever charge collected on the capacitor, but then it will go down. So in both cases, charging and discharging, the current always goes down. As for the charge, if you are discharging, the charge goes down. But if you are charging it, let's go back to this one. If you are charging it, charge goes up to a maximum value if you are charging it. But if you are discharging, the charge goes down with time. And here you can see that this is a decaying function. Now, the charge may go down like this, or it may go really quickly, or it may take longer time to go down. Now, how fast the capacitor is charged or discharged, it's determined by the time constant tau, which is R times C. So R is in units of ohm, and capacitance is in units of farad. If you multiply them, what you get is the units of seconds, which makes sense because time is in units of seconds. So all circuits with timers, if you have a circuit, and if that circuit does something with time, for example, the blinkers or flashers in the car, it lights up every 1 second approximately, right? So there's some timing. So there's some timer. It should be connected to the timer. So all circuits with timers include resistors and capacitors, just like the cars, blinkers, flashers, or turn signals. So if a circuit does something with time, then there's definitely a R and C in that circuit. Now, finally, let's talk about ammeters and voltmeters. An ammeter or ampere meter is for measuring current, and it's connected in series. So if you want to measure the current passing through this wire here, what you do is you cut the wire and put in the ammeter in between. So you cut the wire and connect the ammeter. So this is important. Ammeter is connected in series. You can see that battery, and then ammeter comes next, and then the rest of the circuit. As for the voltmeter is for measuring the voltage, and it's connected to the circuit in parallel. So if you want to find the voltage between C and D, you don't cut the circuit. You connect the voltmeter in parallel like this. You can see that the voltmeter is connected in parallel to this resistor where I want to measure the voltage on it. Now, why do we do that? The reason that we connect the voltmeter in parallel is because anything in parallel, they will have the same voltage. So whatever you connect here, if the voltage here is V on the resistor, it will be again V to anything that you connect in parallel. So if you want to then measure voltage, you have to connect the voltmeter in parallel so that you don't change the voltage. But if you cut the circuit here and connect the voltmeter in series, then you know that if you have circuit elements in series, the voltage on them in general are different, not the same. Now, as for ammeter, why do we cut the circuit and put it in between the terminals here? The reason for that is that we know that the current in the circuit elements is the same when they're connected in series. So if you want to measure the current here, you have to connect the ammeter in a way that it wouldn't change the current. So for example, if you want to measure the current here, and if you connect the ammeter like this, let's say, you connect the ammeter like this, now what will happen? Just because you connected this device, and all devices, they have some internal resistance, so the current, some of the current that you try to measure here will actually leak into the ammeter. So it will go into this direction, and it will change the current on the resistor. But you don't want to change the current here. You want to measure it. So to be able to do that, to be able to not change current, you would have to you have to cut the circuit at that point. Let's say you want to measure the current that goes through this resistor. So you would cut the circuit here, and you would place the ammeter here in series. Because we know anything connected in series wouldn't change the current. And so when you do a measurement by this way, you wouldn't change the current. And there's also this device called multimeter. So the modern multimeters, they have both ammeter and voltmeter. So if you have one of these, you can change this knob to use it as a ammeter and voltmeter. So you can both measure the voltage or the ampere, the current. But as I mentioned here, if you want to measure the current, you have to connect it in series. If you want to measure the voltage, you have to connect it to the circuit in parallel. So that's all for this lecture. So see you guys in the future videos.